the product of these 49 fractions. There's 49 fractions right here. Each of these fractions is less than 1. I guess it's not particularly important to know that there's 49 of them. The first one is the biggest one, 1/2, then 3/4, and so on. They get smaller and smaller. And it's easy to see that there are 49 since we have 98 divided by 2. These are the even numbers in the denominator and the odd numbers in the numerator. And we want to show that it's less than this very small number, root 2 divided by 14. All right. So one way to do it, and this is kind of hard. I wouldn't have known to do this unless I'd seen this solution. But we'll let x just be the object we're trying to find the upper bound for. So call him x, right? Okay. Now what we do is just create a y that looks like this. And notice everything is just one more. All of a sudden the evens are switched to the numerator and the odds are switched to the denominators. And notice we go out one more than the 98. We go out to 99 here. Now the reason we do this is because when you take the product of x and y, you actually get 1/99. And you can see quickly here that this 2 cancels with this 2 right here. Okay. This 3 would cancel with this 3. And the only real survivors are just 1 and 99. 99 and 1 is all that survives the cancellation process. These 2 circled numbers are all that's left when you get this mass cancellation along the diagonal, if you will. Okay, so we get this statement right here, xy is equal to 1/99, and that's clearly less than 1/98. If you make the denominator smaller, it's going to make the fraction itself bigger. Okay, now let's keep going. Now we also have this truth right here. We have x squared is less than xy, and that's pretty easy to see if you just note that this 1/2, okay, is always bigger than than the first one here, right? Okay, or I'm sorry, let me just write it out. We have 1/2 is less than 2/3. We have 3/4 less than 4/5, and so on. Now you can formally prove this. Words, what this would be saying is that n over n plus 1 is always going to be less than n plus 1 over n plus 2. And that's easy to show. Very easy to show by just cross multiplying, right? Very simple. This would be n squared plus 2n right here when you cross multiply, and then this right here would be n squared plus 2n plus 1, right? So it's fairly sharp inequality, but again, if you cross multiply, you get n squared plus 2n is less than n squared plus 2n plus the 1, right? Okay, and that's what's happening right here. 1/2 is less than 2/3, 3/4 is less than 4/5, and all the way across that is true, right? So that explains why x squared is less than xy. All right. Now, but what does that tell us? That tells us that x squared is less than 1/98. I mean, this statement and this statement imply this certainly, right? By the transitivity of inequalities, I guess. But now, if you take the square roots of both sides, folks, we end up with x is less than, 48 or 98 is equal to 49 times 2. So if you take the square root of 49, you get 7. So this would be less than 1/7 root 2. And then the infamous rationalizing the denominator, all right? If you multiply top and bottom by root 2 over root 2, in other words, a cleverly disguised version of 1, you end up that it's less than root 2 over 14, right? So that would be the upper bound. Let's see, is that what we had when we root 2 over 14? Yep, that's what it was. That's what we were looking for, folks. So we just proved it. And I kind of like the idea here. It's to think of setting up the y like this. And then this part right here is obvious, but is it obvious to even try this? And you kind of have to look into your crystal ball and see where this is going to end up, you know. But anyway, I thought it was a nice little idea. Nothing sophisticated, just kind of a clever, sort of sneaky approach. Okay. We are finished. I don't think I left anything out.